Good day to you. This is Anagalactic, bringing you a presentation in quantum mechanics as part of our cosmic geometry series. Now, quantum mechanics is a very well-known term, but I just got a book yesterday by one of my heroes. Of course, every scientist has heroes because we have forerunners, forebears who carved the path. In quantum mechanics, it's led to a cliff. But according to the Einsteinian principle, which is perfectly valid, that is, validatable, you can understand the universe, and quantum mechanics will be understood. Here's one of the men who is a very important name in the history of quantum mechanics, David Bohm. This is the third printing in 1952 of his book that was released in 1951. I just want to show you this page here if you're interested. I got this at a used bookstore. It just wasn't there a couple of weeks ago, and it was there this week. The man who owned this book before me wrote in the answers to the problems. Not all of them, but a lot of them. And that's one of the great failings of mathematical textbooks. I have two huge objections to the way mathematics is presented. Because, after all, science is supposed to be understandable. It's not all for technology. Now, in technology, here you do have to study for many, many years to understand complex algebra, to understand, certainly, the calculus in all of its ramifications. Oh, the calculus is a nightmare. Absolute nightmare. Happily, I've discovered the solution to that whole nightmare, which is one reason I guess I get a bit elliptical in my emotional constitution. I have lived alone for 16 years since my wife died, so one might expect a somewhat emotional constitution of a man of my hypersensitive nature. Aren't we all? All right, so that's David Bohm, Quantum Theory. What I'm going to be doing is just reading from page 1, the preface written by David, and just to give you a tiny bit of background, if you're not as familiar with the name of David Bohm as you think you might or ought to be to understand anything here, don't ever worry. On my station, my videos are self-contained. Now, it is up to you, of course, to participate, that is, to listen, and perhaps check things out. That's what scientists do. You do have to check the facts, ma'am. Oh, yeah. But what I'm going to be doing here is providing what I think is an important linchpin in the understanding not only of quantum mechanics, but an understanding of science, its capabilities, its limitations. Now, what you must never do or assume is to think that science can hit a roadblock. It's a relative roadblock. We already know that the universe is absolutely logical. Quantum mechanics is not an exception to that. It can be understood by the human intellect. It can be integrated into the human consciousness, which, of course, this gets a bit philosophical, but that's what it will come down to. That's why it's so mysterious and even religious. When you're studying the truth that the universe reveals, you're walking on holy ground. That's why scientists have to be very rigorous in their approach, because otherwise you end up with a model that's based on patently obvious mechanics. The sun obviously flies around the earth. Well, yes, you could say that from a superficial point of view, but if you don't know already that the earth is spinning, then you have no way of knowing why the sun is flying through the sky. It's so obvious that you must constantly re-examine your foundational principles because you may have gotten something wrong right at the beginning. Well, I'm just going to throw in a thought for you to consider. If your mathematics, your science, is producing rockets, is producing miracles for humanity, you might be tempted to defend your mathematical basis because it obviously has local applicability. It does. It has applicability to the earth because we have natural resources that we can engineer. And for that you do need calculus. And then if you want to extend your scope by going out into outer space to take a closer look, such as the planets, then you need general relativity. And that is the magnificent accomplishment of spacetime. It enables spaceflight. So I've been over that. I just need to just touch on these topics as we proceed to our present topic, which is the reintroduction. I've reintroduced my geometry dozens of times over the past 3 years. Dozens of times I've given lengthy presentation sequences on the nature of my discovery in geometry. This channel is not about quantum mechanics or cosmology. Well, it is now, but not originally. I'm not a physicist. However, I am what is called a geometer, and I actually had to look this word up to be sure that that's actually a noun, a substantive of a geometer. Well, it's actually a personalization of geometry. A person who does geometry is what? You basically have two choices, geometrician. Well, geometer, when I first heard it, I didn't think that's a real word, although I realized it could become a real word if you wanted it to. Well, it's in the dictionary, so it is a real word, a geometer. That's what I am. What's rather peculiar is a personal note, just from me to you, you know, my mind state in some way. If I'm not a mathematician and I'm not a physicist, why am I talking about the quantum paradox? Because isn't that a little inaccessible to someone like me? Well, I thought so until 3 years ago, and I wasn't studying any of that. Although I was, but I only out of curiosity. I wanted to know what quantum mechanics was. So I read all the books on it, and I mean, a dozen, that's a lot for a young man such as myself. All right, enough personal stuff. I'm going to be reading from David Bohm's 1951 preface. I'm just going to check the date here. Must be either 51 or 52. A couple of years before I was born. So, I mean, I have an extraordinarily high respect for David Bohm, and here's the introductory comment I wanted to make. David, I have to laugh. I hope you appreciate this anecdote. But David Bohm was on highly familiar terms with the Dalai Lama. The Dalai Lama. I have a whole presentation on David Bohm and the Dalai Lama, because the Dalai Lama said that David Bohm was his guru for quantum mechanics, really for science. The Dalai Lama is a fantastic human being. My sister knows him. My sister is actually a Tibetan Buddhist. And when she waves at the Dalai Lama, he looks at her and nods. He recognizes her. My sister's a little remote these days, so we're not sure how close she is to the Dalai Lama. But the Dalai Lama and David Bohm are buddies. Dalai Lama praised Bohm to the skies in a preface to another one of David Bohm's books. So we're talking about some mighty fascinating stuff. If you love life, you just like being entertained. I just find this remarkably entertaining. But in science, we're not really here to be throwing popcorn at the trained bears and tigers. We're just really trying to get the truth of the universe so we can understand it. Wouldn't that be nice? I think so. Okay, let's try this. This is David Bohm, 1951. The quantum theory is the result of long and successful efforts of physicists to account correctly for an extremely wide range of experimental results. All right, this is actually very dense reading for someone like me. I take very seriously how a scientist or anyone, any writer or presenter, how they begin, how they choose to begin. I'm an amateur writer, and so I'm aware that beginning is a critical moment, is the most critical moment of all. In the rapport, or whatever you're trying to establish, a communication channel between yourself and others. All right, this term that he uses, it's a phrase, a wide range of experimental results. Well, the term is experimental results. That's a list. Now, I'm actually a database programmer, manager, and designer by trade. So I tend to think this way, is in structures. And a list is a structure. You Python fans are very acquainted with, there are tuples, and there are lists, and there are other kinds of structures. In all programming languages, these exist. But Python actually enables a strict list. So a list of experimental results means something concrete to me. I can see it in my mind. It's a list. So this is something I need to do. I'm very young in quantum mechanics. I'm not... There's so much to know. But this is David Bohm, okay? So you're not getting this secondhand. He knows every single one of these experimental results. I won't say he helped to contribute to some of them, but he definitely is able to interpret things. And in quantum mechanics, that is an art of arts, is to interpret, because you know what's been said about the quantum mechanical paradox, which is a system of paradoxes. You could say it's just one thing, or you could say it's a lot of things that don't, congeal very easily. But any one of this list of experimental results, any one of them, points out the quantum paradox, which is a measurement problem. You could put it that way, but it's very difficult to put in any one way, because it's not a unary phenomenon. It has to do with two things in relation. That's been intuited, that's been inducted, but not much progress has been made in that area of the two-ness. See, we're used to computing position, which is a one-component number. So a linear number is a position, even if it has three numbers in it. That is the average of three straight lines. In order to get a direct straight line, that's called a 3D position. You can do that in 4D also, but it's complexified. And that's when it gets too difficult for a layman to understand, because if the people who are using that form of conceptualization, which has to do with the basis axis system, one of them is imaginary. It doesn't have the same metric as the linear horizontal dimension, which is a one-component number. But the perpendicular component is not linear. It's based on the square root of -1. All of which is to say that two-componency has been noticed as being powerful. What I discovered is there is a rational two-component number system. And I have to bow my head. I mean, that's saying a lot. And I've taken great pains over 650 lectures to point out that a two-component spherical number system answers a lot of otherwise unanswerable questions. So that's what I'm going to be bringing out in this brief video presentation as we go through very meticulously, and forgive me, but this is how I think. We're going to go through this, and I'm going to try to go swiftly, but you can see that I'm not probably going to go swiftly when I stop after the first sentence. This is a 600-page book, and you can see it's very small print. But his objective in producing this book was to give a non-mathematical interpretation of quantum physics so that it can be talked about in some language like English. And for a man who's not talking about mathematical approach, you can flip to anywhere in this book and there are integrals and derivatives just flying all over the place. But I scanned this book before I read it. It is dynamite. Absolute gems, just gem after gem after gem of intrinsic insight into what is this goddamned paradox that baffles our greatest minds. Einstein, Dirac, Feynman, they all died frustrated and angry men because they couldn't understand the fine structure constant, the anomalous magnetic moment, and the collapse of the wave function. Just seemingly defying special and general relativity. You have entanglement. The first word out of the mouth of Dirac when he wrote his book on quantum mechanics was superposition. I discovered the mathematical and geometric basis of superposition itself. I won't say you don't need Ket notation. That has to do with the computation of the wave mechanical phenomenon. Either in a time-dependent or time-independent form, it just gets really weird because of time divisibility. And time is the lacuna. We just don't know what time is. I do. Geometrically. All right, well, that'll be in the next presentation because I want to get through this. There's so much to cover. Because it's so integrative, it's so... Let's go on. An extremely wide range of experimental results are successfully accounted for, according to Bohm, which the previously existing classical theory could not even begin to explain. In other words, this is brand new from the point of view of Newtonian mechanics. There's something from Oz. We're not in Kansas anymore. Well, that's what we need to solve. That can't stay that way. Einstein said that. He's right. It's not that there are hidden variables. That's actually been disproved, but it's a technical disproof of a certain kind of variable. I've found out what the limiting factor is in the hidden variables approach of Einstein. The reason why it can be asserted by Einstein and Rosen and Podolsky, the EPR document, that just really upset a lot of theorization because you can't refute Einstein. Well, then along came John S. Bell, a genius Northern Irish. He's well respected by all because he really came up with the very first experimental approach. This is now science again. He was basically continuing science when no one else could. The wave equations of Schrödinger, Dirac, Heisenberg, and there were at least one other one, were all mechanical explanations of something that really doesn't obey mechanical principles of Newton. But then John provided a framework on the basis of his inequality theorem, which is now absolutely top of the list famous among quantum mechanical physicists. He showed a way to test the hidden variables theory. However, on analysis, and I say this in all due respect, John was operating from within the labyrinth. And I discovered, in a word, that labyrinth is single componency numbers. That's linear numbers. That's Euclid. Because all the numbers we use are one component numbers. Well, that doesn't work because the phenomenon is not a one componency phenomenon. And so the secret to that is to get the geometric relation so you can reestablish a mathematical relationship between two components which seem to have no relationship except you can see that physically they do. This is time and space. Okay? But they're linear time and linear space. That's the problem. Space is not linear. It can be linearized. And we've done that for 2,500 years, you could put it that way. But actually, we've been fooling ourselves. That's a local solution. That works on Earth. But if you need curvature, you will then need the calculus, and that's when you know. That's when I knew. Well, this is in retrospect, but you can say now that once you were forced to the calculus and then to complex numbers, that shows perfectly that your number system is wrong. If you need calculus, your number system is incorrect. See, that can be argued by technologists. No, it's not incorrect. It makes lasers, rockets, and everything else in technology. Yes, it does. But what it can't do is engineer the universe. Because of the two limits. There's a limit going out, which is spatial, and there's a limit going in, which is also spatial. We can't see past a certain tininess. Well, that makes sense, but you want to get as far as you can, so you'll have the basis of the universe. That's where we're stuck. Well, then you can try looking out to see where the edge is, because you have to have a center or an edge. Now, for a geometry, well, that's the answer right there. That edge is spherical. I proved that in 2022. And from that, I proved that the center of that system, of the infinite spatial universe, has an infinitesimal spatial center. But it's not just space. You can't compose it with a one-component number system, but what you can do is prove that your linear number system is embedded in a higher space. That's what I proved with the second theorem. First, the line is embedded in the sphere. That's been known, but it's not been utilized. And it has a specific constant relationship on an irrational number called tau, which we call pi because pi is simply half of tau. But the relationship between the radius and the circumference of a circle is tau. That's strict. That's Loctite, except for the fact that it's an irrational number, because that's not on the line. An irrational number is not on the line, because it has no exact position. Now, Cantor spent his life trying to show that you can prove that any irrational number is on the line because it's between two computable numbers. But by doing so, Cantor essentially discovered the quantum of the system, which is a one-component number which only is linear. And that also involves the notion of zero, which is a second problem, but they're related. If you can switch to a two-component number system, you can get a higher order number space. That's pure mathematics. If you're using a two-component number, you have access to a higher space. That's why we use 2D for the plane, 3D for volume, and 4D for spacetime. You're increasing your scope of your geometry with each linear extension. But that's the wrong thing to do. You don't want to make your linear system extensible. If you do, you get all the miracles of technology, so no one can say that that's wrong. But it's limited. It's superpositional. All right, let's finish this out. It is not generally realized, however, that the quantum theory represents a radical change not only in the content of scientific knowledge, but also in the fundamental conceptual framework in terms of which such knowledge can be expressed. That's called geometry. He just defined the purpose of geometry in relation to mathematics. Geometry is a higher integration of what we conceive to be numeric space. We need the numbers or we can't compute. That's basic. So we're stuck with the linear numbers, but we've already proved that you can extend the linear numbers. It's not just 1D, 2D, 3D, and 4D. You can also complexify it with the use of mathematical imaginary space. That actually gives you the ability to simulate continuity. And I covered that in the last presentation. Let's go on. The true extent of this change of geometry, this change of conceptual framework, has perhaps been obscured by the contrast between the relatively pictorial and easily imagined terms in which classical theory has always been expressed. Now, what David is saying there is that our language system, to express these physical phenomena, is limited in its terms. That it's now insufficient to address the space being addressed. So it's a mathematical problem. But if you say that, you'll never get out, because you'll use your mathematics to try to solve the mathematical problem. But the problem is not your mathematics and context, which you think works, but here does not. The reason your mathematical system does not work any longer in context is that you're not addressing linearizable space. At the quantum limit, which includes, believe it or not, the edge of the universe, that's also a quantum limit on an integration. It's the quantum of the universe, okay? That is a quantum of some kind. We usually think of the quantum as being incredibly tiny, but it has a reciprocal that's incredibly large. And Alexander Unziker is currently exploring Einstein's thoughts on that. So this is all cutting-edge, current, theoretical. It's where we're at that we need to get beyond. We need a solution to all this, you understand? Okay. Well, I found it. We're using the wrong geometry. If we look at the universe the way it was discovered in the 20th century, it's obviously spherical. The proton, electron, photon, they're all spherical. The atom is spherical. We know that for sure. Stars are spherical. Why? You can explain that with gravity. And galaxies are spherically oriented, although spiral galaxies are obviously flattened. That needs to be explained on the explosion of the supermassive black hole, which I discovered in astrophysics. So this goes all the way in both directions in its explanatory value. It's that the universe is spherical, but we're still using Bronze Age numbers. It's just a remarkable thing to be able to say. I am so honored by the universe to have been the man to have discovered this. But in science, you're under orders, you're under oath. I accept this absolutely. You have to share it. Is it just for me to know? So far, yes. But I don't think that's correct. I think I should be speaking up. Well, I'm trying. I even took an obscene approach lately. It only lasted 2 days, then I got some more beer, and now I'm fine. More beer, more tobacco, more marijuana. Oh my God, what's next? Cocaine, meth, shooting up, pills. No, I'm too old for that. I'm probably, never mind. Never mind about me. No problem there. All right. And I have asthma, sorry. All right. Relatively pictorial, well, that's geometric. Easily imagined, that's geometric. In which classical theory, is grid, no, that's not going to work. with a very abstract and mathematical form in which quantum theory obtained its original development. Now, that's a significant statement, but I'm going to gloss over. I'll let you maunder that. So strong is this contrast. What is the contrast? Between the way we're accustomed to measuring things and the measurability of the thing you're trying to measure. It just won't comply. Doesn't have a position, doesn't have a momentum, but it kind of does. Well, it's because it's both. You're trying to get position and momentum where you're accustomed to be able to say we can get a position on a particle. That's what a particle is a position. Well, it's also a momentum. It turns out that is absolutely profound. Because motion has to do with time. I hope that tantalizes you. So strong is this contrast that an appreciable number of physicists were led to the conclusion that the quantum properties of matter imply a renunciation of the possibility of their being understood in the customary imaginative sense. When he says imaginative, he's referring to the human perceptual system, which is based on vision, but blind people have proved that you don't need your eyes to have visual perception. You can perceive, just not the way people with eyes do, but could be better in this case, and I take that approach. We may need more blind physicists because they're going to be able to use their imaginative, that's geometric. All right, and that instead of geometry, instead there remains only a self-consistent mathematical formalism. Self-consistent mathematical formalism that is no longer self-consistent? I think you see directly what the answer has to be. You're assuming that your mathematical formalism is self-consistent. Well, the reason that it's not is that it's a one-component number system. You have to have a number for both space and time because they're never separated. It's like electroforce and magnetoforce. They're the same thing in some sense. What's this duality, this two-ness? Well, you have to be able to put these two things into geometric correlation. That's what I did. They're perpendicular. Albert simply, I don't know how he did this, but he imagined somewhere in the geometry of Albert's visual perceptual system, he saw, while space is linear, time is a problem for clocks, and so let's make time linear. And they're perpendicular. Well, that's part of the answer. I discovered the root of what Albert visualized. It's the perpendicularity not of time and space. It's the perpendicularity of spherical. He perpendicularized, linearized time with already linearized space. We believe in our mathematical formalism that space is linear. Well, I think you realize that's the error. Space is not linear. We can linearize it to get distance. That's all we've ever done. That works. Well, it doesn't work in quantum mechanics because at the limit, the infinitesimal limit with its reciprocal, the edge limit, these are the integral and infinitesimal quantities, which are actually perpendicular. I proved that too. Well, this goes so deep that I don't want to sound like I'm going to Lululand. Maybe time for my coffee. I haven't had coffee yet, so forgive me. I'm highly dependent on certain legal drugs. This is a 70-year-old man barking at you. Well, lucky you. Oh, there we go. We're going to finish the first paragraph of the preface of David Bohm's 600-page book. Isn't that a wonderful ending for a half-an-hour presentation? Self-consistent mathematical formalism which can, in some mysterious way, predict correctly the numerical results of actual experiments. You realize that that's not actually true? Well, it's not that David's lying, it's that he's purposely, or, I don't know, perhaps necessarily, leaving out something. Because this is the whole bone of contention between people like Kastrup and Maudlin. They argue exactly about this. Oh no, our mathematical formalism makes correct predictions. Albert Einstein, from his grave, will continue to say, no it doesn't. Those are probabilistic. Say, but it gives us the results that are accurate. Albert, no it doesn't. You don't know even how it happened. So that's the end of our reading. Hope you enjoyed that. We'll have more on David Bohm and on this geometry, but if you are curious about this geometry, I am devoted to producing. It'll be a LaTeX document, but I'm not going to submit it right away. I'm going to put it out on Google Drive, which a lot of people are afraid of because of the paranoia. I'm beyond paranoia. I just put everything. Go ahead and steal whatever you want. I don't give a shit. Well, you may be more practical than that. People don't like the openness of Google Drive. Well, this is just typical. Because you're exposed. It's like you looked at this wacko's document, then you're in wacko land. You're associated with a wacko. Well, why would you want to do that if you're trying to get ahead in this world? I'll just give you a little tip, honey. Just so you can orient yourself as a real man. And if you already are, forgive me, but if the shoe fits, wear it. You have to forget about your own life if you want to be a discovery scientist of the highest order. If you want to serve technology, serve the Godfather, serve the government, serve the destruction of this world, just be a hypocrite, that's fine. You're allowed to do that, I don't care. But if you're looking for the truth as a real man is, then you're under orders. You will obey the rules, and I'm here to make sure those are enforced for me. I have to make sure that what I say is true. So I get a little edgy when I'm totally ignored for 2 years. All right, so now you know something about your professor. Jesus Christ, the poor man. By the way, this black spot, it's been there for like 4 years, so I continually wonder if it's just going to blossom into cancer because of the tobacco I stick under my teeth. This is not yet. I don't care. My wife died 16 years ago. When I die, I'll die happy because I'll be closer to seeing her again. And you know, that's just emblematic. That's like Rumi or Omar Khayyam, just longing to be back with the ineffable one, longing to be back with true love. You're not going to get it here, except from Anago. So we've gone from obscenity to pure romance. Here we all are having a love fest. Well, it's dog eat rat if you don't get it right. We'll be right back.